Hello students, in this video we'll discuss properties of a matrix A and A transpose A, the symmetric form that's associated with A. So let's suppose we have a matrix, suppose that A is an m by n matrix, right, so not square, then form the matrix A transpose A, right? And so what can we notice about this matrix A transpose A is the first thing we can remark, is that A transpose A is symmetric. Okay? And so we're going to try to understand properties of A in terms of this A transpose A matrix over here. So in other words, well, first of all, what's the dimension of A transpose A? Well, this is going to be an n by m matrix over here, since I transpose it, times a m by n matrix times an m by n matrix. So the overall result of A transpose A is an n by n matrix, right? So the dimension is a little bit different. It's still symmetric though. Of course, here's the proof of this fact. The proof of this fact is if I do A transpose A and transpose it, I get A transpose and then A transpose transpose. But the transpose is an involutive operator, so the transpose, double transpose is just A itself. So it's just A transpose A, and that proves that A is a symmetric operator, right? That's beautiful. Now, the next thing I want to prove is the following. That's the first sort of remark. Now, the first proposition we have about this A transpose A is this proposition, which is going to help us out a lot, is that the null space of A is the same as the null space of A transpose A. So these two matrices have the same null space. So let's prove this proposition over here. So the proof goes as follows. Let's prove it. Proof. If X is in the null space of A, then A transpose AX, well, that's going to be 0 since X is the null space. So this is going to be A transpose of the 0 vector, and that's just 0. So that says that X is in the null space of A transpose A. Beautiful. So in other words, we have one containment over here. We have that the null space of A, hence the null space of A, is contained in the null space of A transpose A. And now let's prove the opposite inclusion, right? And so the opposite inclusion goes as follows. So if what? If X is in the null space of A transpose A, then A transpose A X is the 0 vector, the n-dimensional 0 vector. Okay, great. And now what I'm going to do is I'm going to take the dot product of this expression with X. So that therefore X dot A transpose A X is equal to 0, because this vector itself is 0, so when you dot anything with 0, you get the 0 number. And now I'm going to take the transpose and put it over here, right? And so this implies that A transpose transpose X dot A X is equal to 0. But again, by the involutive property of transposes, this is just A. So I have that AX dot AX is equal to 0, which is equivalent to saying the norm of AX quantity squared is equal to 0, and this implies that AX is equal to 0 because the only norm 0 vector is 0 itself, and therefore what? And therefore X is in the kernel or the null space of A, and we have the opposite inclusion. So we've just proven our proposition that the null space of A is the null space of A transpose A. Great. Now we get an immediate consequence from this, and namely that they have the same rank, right? So let's prove that proposition next. So the proposition is that the rank of the matrix A is the same thing as the rank of A transpose A, okay? Okay, so how do you prove this proposition over here? So proof by the rank nullity theorem. What can we say? Well, let's call these common values of nullity, let's call those common values over here, let's call those common values X, right? Then X plus the rank of A has to be the dimension of the input space. The dimension of the input space is n, right? And then also by rank nullity, X, which is the nullity of A transpose A, X plus rank of A transpose A is equal to n. And so the conclusion, therefore, since the x's cancel out, therefore that says that the rank of A is equal to the rank of A transpose A. Excellent. Okay, now we get an immediate consequence of this too. What's the consequence that we can conclude from this? We can conclude from this that what? Apply this result with A changing place with A transpose, right? So in other words, I can apply this theorem over here with A being replaced with A transpose, and what we get as a result of this? We get as a result of this that the rank of A, which is the rank of A transpose, because I know the rank of A is the same as the rank of A transpose, is the same as the rank of A transpose A transpose, which is just the rank of A transpose, right? So we have this beautiful result over here that the following is true. So in other words, we just proven that the rank of A is the rank of A transpose A is the rank of A transpose. So all three of these matrices have the same rank. Now this, of course, is a what? That's an m by m matrix. This is an n by n matrix, and this is an m by n matrix. So the rank is preserved for all those different structures of the matrices. Beautiful. So we have this result over here. So this is equal to this is equal to this. We have all these rank relationships over here. Now we can also show, of course, as an immediate consequence of these inequalities over here, is that the row space of A, is the same as the row space of A transpose A, and the column space of A transpose is the column space of A transpose. Okay, just by applying these rank inequalities over here together with the inclusions of the rank operators. So we're going to see in further videos that once I have an m by n matrix, this matrix over here, A transpose, is going to play an essential role in understanding the singular value decomposition of the matrix A, which is a generalization in some sense of a diagonalization argument for when you don't have a square matrix. And so we're going to see in further videos how that factorization plays into how these inequalities over here, in terms of the null spaces and the ranks of these matrices, play an important role in understanding the singular value decomposition. Thank you very much.